So if I can have the slides, it's a great pleasure to talk here, particularly do this in honor of the contributions of Georges Lemaitre. We just said he's the father of the Big Bang, but we should have a different term, and I think he proposed both the term primordial atom and cosmic egg. So perhaps we can work to have these terms live on. Particularly, I think it's challenging to do this in the company of some of the true architects of modern cosmology, that is the speakers before and after me, and to do and capture for you 14 billion years of cosmic evolution in 20 minutes. I want to actually focus mostly on the quantum mechanical aspects, because as you know, we have these two great theories, relativity and quantum mechanics, describing the very large and the very small, but they do this in entirely different language. Even if we think about the mathematics of general relativity in cosmology is geometry, curvature of space and time. The mathematics of the quantum theory is the theory of operators, algebras, and probabilities. Yet, I think the great questions, and I will be raising more questions than answers in modern cosmology, in fact in fundamental physics, are very much about the interface of these two theories, which is basically an area of wide speculation. And I will take you on a tour of that arena. Of course, Einstein's equation, here is the 1915 version without a cosmological constant, is wonderful in the sense it's tying together two completely different realms. On the one hand, we have geometry. On the other hand, we have mass and motion. And just in terms of a simple slide, you can say that on the one hand, mass will tell space-time how to curve. Presence of a massive object curves space-time in a very particular fashion. And then that curvature of space-time tells how mass should move. And that's basically the slogan that captures relativity theory. Now, as we're discussing, the most spectacular result of that theory has, of course, been the expanding universe, which is now studied and understood in great detail, but also raises many important questions. In particular, the questions of singularities, the fact that, what's the beginning of time, how do we deal with space-times that are not smooth? And this is a wonderful quote by John Wheeler, one of the central, I think, scientists in reviving the theoretical physics community's attention to gravity, that how can the existence of space-time singularities represent an end to the principle of sufficient causation and the predictability? How could physics lead to a violation of itself? That is, how could physics lead to no physics? Of course, from a point of view of physics itself, it's exactly these paradoxes, these singularities that draw our attention and are usually a good place to look into the beginning of the next chapter. In fact, if you think about singularities in the cosmic evolution, there are two. There's the initial singularity of the Big Bang, but there are kind of final singularities in black holes. And I actually want to use this occasion also to say something about black holes, because black holes in some sense mirror images of the Big Bang singularity, which signify not the beginning, but the end of time. In fact, if I can allow myself a few slides, black holes, of course, are this moment well known to exist in various varieties in our universe. They are a very important topic of study. But mathematically, they have a very special property. If you think of the space-time picture, here time is flowing upward of an imploding star, it will create a singularity, but the singularity is shielded by a so-called event horizon, a sphere around the singularity of a certain radius, the Schwarzschild radius. There's a nice formula for that. It's proportional to the mass of the black hole. And the way to think about this is that time is actually switching its direction inside the event horizon. That's flowing in a radial direction. That is to say, inside a black hole, there's only a finite amount of time. And the singularity, therefore, has very much the similar nature as the singularity of the origin of the universe. Now, if we study the universe, let me just see, the end of time, yes. This is a difficult, here we are. Jim already mentioned this. Important part of cosmology is studying, in fact, inferring the composition of the universe, and these are the current numbers. So we have the known matter, 4%, the so-called dark matter, 23%, and then the remaining dark energy, which we hear much more about in a moment. But all of them, the understanding of them definitely involves quantum mechanics. Again, they are appearing in this kind of extended formula of general relativity's fields equations. Dark matter, as we just heard, it's basically big clouds surrounding the existing baryonic matter. If it indeed is matter, I should say there are various theories, very unsuccessful at this moment, but still speculative, that it's actually should be seen as a variation or a different version of the laws of gravity. But I mean, we know there's a huge amount of dark matter that manifests itself in the structure of the universe. And the dark energy, which again we'll hear more about, is a kind of vacuum energy present in the empty space. Well, to understand that from a theoretical perspective really drives us to understand more the quantum mechanical basis of theory. And again, to remind you, of course, in classical mechanics, we think of particles moving on straight lines. There's determinism. There's a principle of least action that determines the particular path that particles take, or general dynamical systems, whereas in quantum mechanics we have a very different picture. We compute probabilities that in Feynman's path integral formulation can be written as sum over histories. So in quantum mechanics there are natural fluctuations that actually provide a wonderful way to describe the microscopic nature of the universe. In fact, the important way to think of elementary processes, for instance in particle physics, is through these elementary interactions, as in this particular Feynman diagram, particles moving in space and time and exchanging intermediate particles, for instance like this photon here exchanged by two electrons. These are virtual particles, particles that you cannot actually detect in experiments, but are very important in the construction of the theory. In fact, there are many other processes, and a very important process is this process, a process where out of vacuum a particle and antiparticle pair is created. It lives for a very short time and then decays again. Its effect itself is not measurable, but it has an indirect effect. And the indirect effect is of these pairs of virtual particles is that they, basically this is I hope you admire my PowerPoint technique. This is a visualization of the vacuum, which is sometimes a boiling pot at the quantum mechanical level of all these virtual particles coming in and out existence. And in some sense that follows the rule, I think, Gell-Mann's rule, that in quantum mechanics everything that's allowed is obligatory. So all possible processes happen in these kind of vacuum structures. And the vacuum is a very exciting place. In fact, its effect of all these processes is the presence of an energy that would be the cosmological constant explanation from a quantum mechanical point of view. But in fact, the measurement of that cosmological constant that you can think of as proportional to 1 over the radius squared, essentially, of the universe, that's the Hubble scale, is incredibly small compared to the natural unit to measure this process, which is the Planck length. I will say something about this in a moment. It's a famous result because the observation is a factor 10 to the minus 120 smaller than the calculation, which must be the largest theoretical mistake ever made. In fact, one way to think about it is that space-time itself, according to the rules of quantum mechanics, should have fluctuations. And in fact, the size of these fluctuations you can calculate by looking at Newton's constant, G Newton, in fact, which has, after the right combination, dimension of length squared. And so there's a natural length associated to gravity, which is the Planck length, which is the smallest length that we know in physics. It's the fundamental length scale of space and time. And so one way to think about this is that space itself has some kind of granularity at this Planck scale. So the big picture to understand cosmology and fundamental physics, the following. So the smallest scale would be the Planck scale at 10 to the minus 35 meters. The largest scale is the size of the visible universe, roughly 10 to the 25 meters. for the biologists among us, they are very comfortably right in the middle. And to get an idea of the other scales, this is as far as we humans have explored the solar system, roughly the distance to the moon. And this is the distance to which our particle experiments have extended. That's roughly the scale where the current particle accelerator is operating. So in some sense, this is the part that we have mapped out in physics. And clearly there's this huge microscopic scale yet to be explored. Yet we feel that at the very left-hand side of that picture, some of the mysteries of quantum cosmology should reside. Going forward, I mean, we already heard about cosmic inflation. Cosmic inflation is a very speculative idea of a vast expansion somehow just before the hot Big Bang, where in a fraction of a second, in fact 10 to the minus 35 seconds, the universe was magnified by at least a factor of 10 to the 26. And why we find this interesting is that that might be a way to connect the shortest and largest distance scales in the universe. And in fact, if this theory worked, the very elegant mechanism is that the quantum fluctuations at the microscopic scale might be rapidly kind of magnified and frozen in and provide the kernels of the microwave background fluctuations that we just heard about. So it's a speculative, but I think it's a theoretically very attractive idea. Another attractive idea is directly related to Stephen Hawking's work, which is that how do quantum theories behave in the presence of singularities and gravitational objects? And what he discovered is that if you have these, again, we look at the property of the vacuum, so we look at these particles that can appear out of nowhere. If they come in the vicinity of a black hole, in fact, in the vicinity of the black hole event horizon, then in a cartoon fashion, some of these particles can be born on the left-hand side and the other on the right-hand side, or the inside of the horizon, and therefore the green particle here is kind of allowed to escape. In fact, you can make a much more precise calculation, and you find that black holes, at least in the long term of microscopic black holes, very rapidly, will evaporate by sending out thermal radiation, where a temperature that can be calculated, and in fact it's equal to the surface gravity of the black hole, and again there's a nice formula for that, it's proportional to 1 over the mass of the black hole. So it's only something that is, say, observable at very, very, very tiny black holes. But actually this kind of black hole, the quantum mechanical properties of black hole might provide the most important clue how we should think of space-time at microscopic scales, which again is important for early cosmology. And in fact, since there's a temperature, there's also an entropy you can assign to a black hole. It's again a famous calculation done by both Stephen Hawking and Jacob Bekenstein, with a beautiful result, because the entropy of the black hole, that is kind of the information that could sit inside the black hole, turns out to be proportional to the area of the horizon in natural Planckian units. So in some sense, often the cartoon version again is that you think of the horizon of a black hole as kind of a digital storing place, where there's 1 bit per Planck length squared. So clearly information and quantum gravity play an important role in understanding the quantum mechanical properties of black holes and singularities. And one way to understand that, and this is where string theory comes in, that another prediction of general relativity is that gravitational waves will appear. They have, of course, been detected last year. And at a microscopic level, these gravitational waves would behave like quanta, and so they would be like particles that you could scatter. Well, gravity is, from a particle physics point of view, a very ill-behaved theory because of, as I said, the Newton's constant has units of length squared, or 1 over energy squared, and it means that the interactions between gravitons grow at higher and higher energy, and they are an example of a non-renormalizable quantum field theory. Well, string theory is one way approach to kind of soften that singularity and make it into a well-behaved theory of quantum gravity. And I won't say much about string theory other than it supposes kind of intermediate, I would say kind of force-like particles, which is the string, a one-dimensional extended object, whose mass will be roughly proportional to the Planck mass. So it's an object that has a kind of microscopic size of this Planckian size, far, far beyond any natural observations that we can make. Well, again, in one slide, how string theory actually deals with black holes is as follows. Gravity is explained by closed strings, so general relativity is kind of a prediction of string theory. And black holes, again in a cartoon-like fashion, can be seen as a different kind of strings, namely open strings that actually kind of reside on the horizon of the black hole. And so string theory gives us a microscopic understanding, at least in certain cases, of the quantum mechanical properties of black holes. Well, taking that line of research to its kind of extreme had led to this famous correspondence. That's the work of Juan MALDACENA, member of this academy, and many, many others, that tells us, gives a correspondence of quantum gravity in space-time in terms with a different theory, a theory that resides only on the boundary of that space-time manifold, which is a theory without gravity. So that is, for the first time, at least in limited cases, we have working models of a quantum gravitational system. Well, clearly the challenge is, of course, to take these systems and push them to the realm of cosmology. Unfortunately, I think there are many, many, and we can talk more about in discussions, many, many issues that make this approach, which has been quite successful in the context of black holes, less successful, more problematic in the context of cosmology, in particular early cosmology. Because in the same way as the black hole itself was resolved through this kind of holographic point of view, you would like to do something similar for the space-time singularity corresponding to the Big Bang. But I must say one thing which I think is kind of very promising. Now we know that in general in physics, there are two ways to approach physical systems. And one is reductionism, reducing any system to its fundamental constituents, which of course has been extremely successful in the case of particle physics. And in some sense we have seen that the laws at the smallest distances, like the description of the standard model, are so much more elegant than the description at larger scales. But I would say the other half of the physics community has a completely different point of view. So particularly if you were in statistical mechanics or condensed matter physics, you would say life is pretty complicated on the smallest distances. For instance, describing a glass of water in terms of a large array of H2O molecules, a very inefficient way to describe hydrodynamics. In fact, we know that in many realms, the fundamental laws of physics emerge at largest distances. They are in some sense the effect of taking a large degree, set degrees of freedom, and out then come certain mathematical objects that in many ways only are true in the infinite limit. So the laws of thermodynamics are an excellent case. Now one thing we have learned, in particular I think through the study of black holes but also other objects in gravity, is that there's a close parallel between the laws of gravity and the laws of thermodynamics. In fact, they're both beautiful equations, and Einstein, I think, loved them both. I mean, he also really was a great fan of the law of thermodynamics. And I would say kind of the modern point of view in terms of quantum gravity is that perhaps the description of space and time and the description of even the fundamental laws, like Einstein's equations, should not be thought as fundamental, but should be thought of as emergent. So a new point of view is kind of arising, where in some sense relativity, general relativity, space-time geometry, and the equations that go along with it are actually emerging out of other systems, microscopic systems, systems that do not have gravity in them, but actually are described perhaps in some sense in pure quantum mechanical language, so in quantum information. So again, this is to a large extent speculation. It would be wonderful, I think that's certainly the hope in the community, that this point of view will shed light on cosmology and also on the cosmic singularity. But in fact, it would be in some sense in the kind of battle that I set up in the beginning of my talk, where I think to make progress we have to unite the quantum theory and the theory of relativity, so kind of unite algebra and geometry, that perhaps algebra or quantum mechanics might have the last word. Thank you very much.